We have been talking about induced EMFs due to changing magnetic fluxes. Well, this brings us to a good point now to talk about transformers. Now, let me start off with a quick story. Nikola Tesla is very famous for his work with electricity. He was able to understand very well the workings of generators, how they produce electricity, and how to transmit electricity. He was an employee, one of the brightest employees of Thomas Edison, who ran the largest power companies in the Northeast United States. But while he worked for Thomas Edison, he discovered something about alternating currents and argued that alternating current was better to generate and send out to the general public. But Thomas Edison argued that direct current was better. Well, this became a very heated debate to the point that Tesla left Thomas Edison's company and formed his own power company. So who was right? Well, let's look at what Tesla's argument was, at what he discovered, and then we'll answer this at the end of the video. So the key to this question is in a transformer. You've probably heard about transformers. You watch videos of big storms and you see big sparks flying and someone says, "Oh, a transformer blew." What is a transformer? Well, a transformer is just a device that consists of two coils of wire, both of them interwoven and linked to an iron core. And the way it works is if you have a changing EMF in one coil, then that induces a magnetic field which propagates through the iron core, induces a changing magnetic flux or magnetic field through the other coils. That changing magnetic flux then induces a current, induces a voltage in the second coil. So when you have a changing EMF in one coil, it induces an EMF in the second coil. Now, here, of course, are the equations from Faraday's law. The voltage of one coil is going to equal negative N, where N is the number of coils, times the change in magnetic flux over the change in time. And that equation is valid on both sides of the equation. But you can change the voltage based on the number of coils you have. Notice the change in magnetic flux is going to be the same on both sides. So if you change N, then you're inherently going to change the voltage. So it turns out that the ratio of the EMFs is going to equal the ratio of the number of turns in each coil. So the voltage in your secondary coil divided by the voltage of your primary coil will be equal to the number of secondary coils divided by the number of primary coils. So we can either take our transformer and use our, in the secondary coil, add more loops, which will increase the voltage because they're directly proportional. Or you can have fewer coils in your secondary coil, thus decreasing the voltage. What you have pictured here is a step-up transformer. Because there are more coils in the secondary coil, you're going to increase the voltage since they are directly proportional. The other way to look at this is using our ratio, where the ratio of EMFs is going to equal the ratio of numbers of loops. And if you increase the number of loops in the secondary coil, then you have to also increase the voltage as well in that secondary coil. Now, throughout this whole process, energy must be conserved. And since energy is conserved, we can plug plug in our ratio of EMFs to ratio of numbers of coils and apply that in a couple of different equations, and you end up getting that the ratio of currents is the inverse of the ratio of number of turns. Notice that the ratio of current in the secondary coil divided by the current in your primary coil is going to equal the number of turns in your primary coil divided by secondary coil. There, it's inverted. And so the ratio of currents is going to be the inverse of the ratio of turns. Okay, so this is a pretty cool little device. We get to have one voltage and then all of a sudden change that voltage into a second voltage. Here's where this principle gets really useful. When you transmit electric power, energy is always lost due to resistance. And this loss is greater when currents are higher. Remember in our discussion of electric power, we came up with 3 different equations. Power is equal to current times voltage. Another one was power is equal to voltage squared divided by resistance. This is the third equation that we came up with, that the power is equal to the square of the current times the resistance. And this is a very good equation for describing how much power is lost in the transmission of electricity. When you have high currents, then you have high power loss. So if you have a current and then you double the current, you actually quadruple the amount of power that's lost during transmission because of that square function in there. All right, so we want to minimize power loss. How do we do that? Well, transformers can change the current so that we minimize the amount of power that's lost in transmission. If we use a step-up transformer, meaning the number of coils in your secondary coil increases, so we have a step-up transformer, then as a result, your secondary current has to drop. And if your secondary current drops, then that means the amount of power that you lose also drops. So the key is to transmit energy at a very high voltage. The higher the voltage, the lower the current. And when you do that, when you're at high voltage, low current, then the amount of power that's lost in transmission is minimized. Now, one very important note here, and this is the whole answer to the Tesla versus Edison question. Transformers can only work if currents and voltages are changing. When you have a direct current, you're going to have a constant voltage and a constant current. But with an alternating current, your voltages and currents are constantly changing. And this comes in, let me come back here. This comes into the fact right here that in order to induce a current in the secondary coil, there has to be a change in magnetic flux. So you have to have a change in magnetic flux of the primary coil. You're not going to have a change in magnetic flux unless your voltage is changing. So that is why only alternating currents work in such a situation like this. So here you go. Here's the whole picture. This was Nikola Tesla's picture, and this is actually what we use today. You have a power plant that generates alternating current. That alternating current is produced at some voltage. You have to send it through a step-up transformer, which increases the voltage to something really high, like 240,000 volts or something. And it's transmitted over long distances at low power loss because the current is low. And then when you get into city regions, you hit a substation. Those would be the gated areas that have lots of high fancy electrical equipment in there. It's called a substation. It's full of step-down transformers, so it decreases the very high voltage electricity to something that's more manageable, and then it's distributed throughout the cities. And right outside of your home, there's another step-down transformer, which drops it down to 200 volts if you're in most countries around the world. Here in the United States, it would drop you down to 120 volts. So let's answer our question. What's better, alternating current or direct current? Tesla argued that alternating current was better because it allowed us to transmit energy to further distances. But Edison argued that direct current was better because all of our appliances run on direct current. You can't run a vacuum cleaner or a toaster or an oven. You can't run them on alternating currents. So direct current is important. So this was a very heavy debate. Well, it turns out that after Nikola Tesla died, Thomas Edison looked a little more into Tesla's arguments, and Tesla was right. So Edison started adopting alternating currents, and we still use alternating currents with AC to DC adapters or converters. If you have a laptop or some device where there's a big black box somewhere along the cord, that is a converter so that it can it can convert alternating current to direct current, which is what all of our appliances and devices run on.